So I'm a assistant professor in UC San Diego, which is not far from here, 2 hours. And then I direct the Spatiotemporal Machine Learning Lab. So the logo about my lab was designed by my student. And there is an SNT, which stands for Spatiotemporal, and there's also a rose in the logo. So there you go. The focus of our group, because we're in computer science, and the focus of our group is about designing algorithms and models for capturing insights from large-scale spatial temporal data. So the type of applications we work with, including public health, we work with CDC to forecast COVID-19. We work with climate scientists to accelerate their climate models. So for all kinds of fields. The focus here is really about spatial temporal dynamics. As you can see here, the type of data we face in these different applications are not traditional image data that are static or text data that is discrete. The spatial temporal data is highly dynamic and also continuous. So that poses a lot of challenges to existing machine learning frameworks. That's what we're trying to solve, is to design machine learning algorithms for spatial temporal dynamics. So one tool that we bumped into is Symmetry, and a lot of you guys are much bigger experts in this topic than me. So there has been a lot of success of Symmetry in image data, in graph data, for protein folding, and in physics for high energy physics data. And there's a lot of work here. For example, test work, and Max is a huge expert in this. A lot of papers from your group, and we also read closely Frank's paper on equivariant flow models. And we were asking the question, like, how about spatial temporal dynamics? So here we're really looking at the forecasting problem, where we have the past states of a system, and we wanted to predict the future state of the system. And in this case, we assume we don't know the underlying mechanism of the system. So very much like a data-driven approach to learn the dynamics and then move the dynamics forward into the future using data. Okay, so that's kind of the start of our journey. We wanted to look at forecasting, but we wanted to forecast very complex turbulence. So that's a very good start, right? It's the hardest problem in forecasting. And the motivation for that is we wanted to design a deep surrogate model that can mimic the dynamics of this type of complex fluid. So Max mentioned there recently has been a lot of development in surrogate models for climate models, but one of the fundamental limitations is that these models don't generalize. So they're often trained using the data from a specific initial and boundary condition, but then when you apply these models to systems of a different initial and boundary condition, they will often fail. So we started out this research by asking the question, can we develop models that are actually generalizable? And we did a very simple test here, where this is looking at forecasting. So we try to forecast very simple sine functions. Let's say we have some training parameters drawn from interval A and B, and then we have some testing parameters drawn from the same interval A and B. The prediction task is as follows. So we have some data from the past. This on the left-hand side of this vertical line. We wanted to predict the future, so that is the right-hand side of this vertical line. And then we wanted to test whether some deep learning models, let's say seek-to-seek models, or you can use transformers, can successfully predict the sine function. And it can, because that's not surprising. It's a very simple task. However, when we look at a slightly different setting for forecasting, where here we have some training data, and the parameters of the dynamics are different from the parameters in testing. So the parameter that controls the sine function essentially includes the magnitude or the phase of the sine function. So when we sample parameters from a different regime, in this case, this is an extrapolation regime. Now, no matter what deep learning models we use, it always cannot predict correctly. So this points out to a very fundamental question in forecasting. which is distribution shift. So if the training data distribution is different from the testing, then deep learning models often have a hard time predicting accurately. And in contrast to typical distribution shift in image data, here we're really talking about distribution shift in terms of the parameters of the system. So the data distribution could be actually similar to each other from training to testing, but the parameters that govern the dynamics are actually different. Now, we wanted to solve this problem. The first idea that come up was that, well, maybe we're looking at physical dynamics. Can we leverage insights from physics to alleviate this issue of distribution shift? So the high-level idea is that even though the distribution have changed from training to testing, the laws of physics do not. So maybe we can incorporate the laws of physics into this system such that the models can generalize. Right? So Noether gives us this nice theorem. She said that for every symmetry, there is a corresponding conservation law, which said, maybe if we wanted to inject the physical laws of conservation into deep networks for forecasting, then we can maybe consider this tool called symmetry. So I had no training in representation theory. Then I was okay, that seems like an interesting thought. Let's try to use it and see whether it can help. So luckily, I have a great collaborator who was my postdoc, Robin Waters. He had a PhD in representation theory. So we started looking into this direction together and see whether we can do something about it. Right? Let's see. So what we mean by symmetry include invariance and equivariance. Right? So now if I have a group, which is some sort of transformation, and then I say a function is invariant if this transformation doesn't change the output, if I transform its input. And more general notion is equivariance. So if I transform the input, this transformation happens on the output automatically. And if a function satisfies this condition, we say it's equivariant. So it's easy to see that invariance is a special case of equivariance, because if I pick the right-hand side of the equation to be the identity, then equivariance will reduce to invariance. Right? So for dynamics, we can kind of look at this image that's similar to what Max showed in his slides. Well, we're looking at velocity field of a turbulence. So let's say if I stretch the velocity field by 2, so magnitude-wise velocity increased by 2, and then rotate, it gives me the same result as if I rotate first and then scale it up by 2. So this kind of transformation determines the property of this function. So when we say equivariant networks, as you know, we're trying to build functions or functional approximators that can approximate this function, and this function needs to satisfy this condition. And we know, well, let's look at the symmetries in dynamics. So how is it different from typical data, let's say image data or text data, right? So first we need to define what we mean by symmetries in dynamical systems. We know dynamical systems can be always described by a set of differential operators, say first order, second order derivative. So we say a symmetry belongs to this differential system is that if we transform a solution, let's say phi the solution of this differential system, if we transform the solution, the transformed outcome is also a solution of the system, then by definition, this differential system have the symmetry G. But this is purely in a mathematical sense, from the mathematical equation sense, right? And based on this definition, we can then derive different symmetries. For example, the 2D Navier-Stokes equations. So these are the governing equations for viscous fluids, which is the focus of this work. So the data we have looks like this. It's a periodic turbulence with periodic boundary conditions. The reason we study this is it really resembles the dynamics of El Nino, where two types of fluids with different temperature interacting with each other. We thought if we study this first as a toy example, we will have a better tool to understand the larger scale climate phenomenon. So here we can derive, according to the definition on the left-hand side, different symmetries of Navier-Stokes equations. In this paper, we give different ways to design equivariant networks for different symmetries in differential systems. But here I just want to give you one example to illustrate how we can utilize the unique knowledge from differential equations to design equivariant networks. So let's say we focus on the symmetries of scaling. But the scaling law derives from here, And then the scaling law looks a little bit interesting because when we scale the space by lambda, then the time actually needs to space by lambda square. So in Navier-Stokes equation, people know this by half space quarter time law in turbulence. And then this actually encodes some unique knowledge of turbulence modeling. And we can actually put this into use for modeling turbulence with equivariant networks. So in general, how do we design equivariant networks? Well, it's actually very similar to how we design a convolutional neural networks. Right? So in convolutional neural networks, we say it's translation invariant because we are actually using weight sharing to share weights along bundles of this little filter. So basically, the filters here and the filters here are completely shared, and then the weights here are freely trainable. So if I move a patch of the image from the top left corner to the bottom right, then I will get the same results in terms of outcome of the filter. So this idea of weight sharing is actually fundamental to the design of equivariant networks. Of course, like here we're only talking about a simple translation group. We can generalize this idea to other groups, and this result was given by this nice paper, Weiler and Seiza, where they said, well, they give a sufficient necessary condition for designing arbitrary convolutional layers that are G equivariant. So if I have a G, right, let's say I have a symmetry group, whether it's translation, rotation, or in other complex continuous groups, then I say, okay, we can design a kernel such that it satisfies this condition called group conjugation, group invariance under conjugation. So this is the equality, and then this symbol here is basically a group representation, and you can think about it as an invertible square matrix. So you left multiply and right multiply this square matrix. If it's the equality holds, we know this convolutional layer is G equivariant. So the art of designing equivariant networks just boils down to solving linear constraints according to this equation, but we can definitely solve it more efficiently. So there's a lot of art in terms of goes into this. Okay, so let's come back to equivariant networks for differential systems. So I'm talking about scaling. The reason scaling is of particular interest to fluids community usually comes from the self-similarity phenomenon in turbulence, right? When we look at the eddies on the coffee or the big waves on the ocean, they actually have some similarity even though they are completely different scales. So if we wanted to design a convolutional layer for this type of dynamics in order to forecast, then we probably need to think about something else beyond the standard convolution. Because the standard convolution doesn't have scale invariance, equivariance. So in order to do that, we need to generalize scale equivariance. We need to generalize the idea of convolution to other groups like scaling. So similar to how standard convolution shares weights across different positions on the image, for scale equivariant networks, we basically need to scale the kernel at different magnitude and then allow the weights to be shared across different scales of the kernel. So you can see this is kind of very analogous to how CNNs share weights for translation symmetry. So for scale symmetry, we can upscale the kernel by different factors. So these are same velocity field, but just scaled by different factors. And then we allow the weights to be shared across different scales, and then the weights within each scale to be freely trainable. And then the final filter is the aggregation over different scales. So in this way, we can obtain scale equivariance. But then we can encode actually the unique knowledge of turbulence into this aggregation, right? Because we know turbulence satisfies this type of, square, square times square, quarter times quarter space, half space quarter time law, right? Then we can use this law as our projector, right? As our scaling operator. So this scaling operator will transform the velocity field W over space and time according to the laws of physics. And then we will aggregate over different scale lambda. Here lambda is an integer. So there's obviously some sort of numerical error because we cannot aggregate over continuous number of scales. So that's one limitation of this work. We have to discretize the number of scales and then being able to aggregate them. And then here is the kernel that takes the input q. Here is a velocity vector. And then that works, we can then basically compute this kernel aggregation and reach an equivariant, scale equivariant output. And we can always compose these type of scale equivariant layers to have deeper layers and then obtain eventually equivariant deep neural networks. Okay, any questions?
I have a question about time though. So the time, so is this a convolution that also goes over time index?
Yeah, so basically we're using 3D conv. So the time is just to us a different axis.
Okay. And is this invariant or equivariant?
This is equivariant. This is equivariant in a sense that here we actually, I mean, it's not showing here, but we actually left multiply and right multiply the same group representation.
Oh, I see. Yes.
Okay. Yes.
Maybe it doesn't matter, but I don't. When you have the aggregation on the right, I'm a little confused about how it's going to work at different scales because it seems like there's going to be different number of filters. Like
yeah, exactly. So it's basically like we have different. So we basically downsample. When you downsample, you like cross-graining the velocity field, and that reach different scales. But then it's limited by essentially like 2 to the multiples, right? So we cannot do like the fractions of scale. That's the limitation of this framework. Yes.
So when you're training your model and you have these different scales, you're basically ensuring that you're coarsening and like sort of with the appropriate length scale shrinkage.
Yes.
So the absolute length scale does matter because it basically controls how you're coarsening.
Yes, exactly. Here we're talking about, I mean, there are two actually scales here for fluids, right? One is that the scale of the video in some sense, right? The image scale. But the other one is the physical scale. So here I'm only talking about the physical scale. And the reason we can use the physical scale is we're actually using this scaling operator from like Navier-Stokes equations. Yeah, so exactly.
Okay, can I ask one more? For time, since it's a factor of 2 different, is the way that you dilate also changing by a factor of 2?
So the way we dilate corresponded to like the video scale. So actually for that we need to use a different set of techniques for velocity field. But here we're not. So here we're not dilating. We're basically just stretching the velocity field. Okay. All right. So then here I wanted to show like how the symmetry can help generalization. Back to our original topic, right? That we're doing a very simple experiments where we upscale the data by different factors from training to testing. So in this case, we'll mimic the situation where we train our data on a particular scale of the turbulence, and then in testing we artificially upscale the test data by different factors. So this mimic the distribution shift that I talked about in the beginning. So it's not surprising that for baseline models like ResNet for video prediction, because it's not aware of this kind of scale change, so the prediction error in terms of RMSE will explode as we upscale the data further and further because the data distribution becomes further and further away from the training data. So the test error will explode, where then equivariant model will be robust in this case. So, and then we also measure another important metric in turbulence community, which is energy spectrum error. So this measures how the energy dissipates in the predicted turbulence field, so that makes sure the predictions are actually physically meaningful. And then again, we can see that the predictions from the equivariant models are actually quite robust on this metric as well. So in some sense, you can say that incorporating symmetry in deep networks for turbulence also can generate physically meaningful predictions.
So can you say a word about how your model actually works? So you say you do a convolution over a 3+1 or 2+1 space-time volume?
Yes.
And then what is the output of your?
So output is actually just next timestamp.
Okay.
And then we do this autoregressively. So let's say if I wanted to predict like 10 timestamps, then we will do this autoregressively using the prediction from the previous timestamps to feed back into this.
Okay, and so you basically convolved into the over time and over space to predict one One
Yes.
time slice or one block in the future?
One time slice. All right. Okay, but then when I presented these results to turbulence community, they were a little bit skeptical because this experiment is a bit artificial in some sense, right? Because we create the testing data in exact perfect group transformation, and then in practice, the data distribution shift may not be this kind of perfect group transformation. So that basically motivates us to the next chapter of this journey, which is to study approximate equivariant networks. So thanks to Tess for highlighting our work in the morning. So basically, we want to say that, okay, it's great that we can incorporate symmetries in deep nets for modeling turbulence, but in real-world data, the symmetry is never perfect. Right? And then I'm using this example here from the SuperSonic jets because we actually do have experiments in this paper to model real-world supersonic jets. And it took us some time to actually obtain real-world turbulence data. And I had to negotiate with people in NASA to beg them to give us the data. But we actually finally got it. And I think we were able, probably the first actually to try this model on real-world turbulence data. Okay, again, work was left by my PhD student, Ray, and my previous postdoc, Robin. He's an assistant professor now at Northeastern. Okay, so then this workshop, a lot of this workshop is about symmetry. But let's sit back a little bit and think about when symmetry is a good inductive bias. Coming for you guys who come from physical science domain, you might love symmetry and you think symmetry is always the best inductive bias. But maybe that's not the case, right? So we can, or Frank can argue asymmetry is better because the polynet is actually using asymmetry rather than symmetry. Right? So okay, but here let's just think a little bit and think about when symmetry is an inductive bias from machine learning perspective, right? So we can say, well, maybe the model is, let's say, how much symmetry is the data should somehow reflect how much symmetry is in the data. How much symmetry we have in the model should match how much symmetry we have in the data, right? Because if we build too much symmetry in the model on this end, where there's not much symmetry in the data, then the model is over-constrained. On the other hand, if there's a lot of symmetry in the data, but your model does not have enough symmetry, then we need to bake in a lot of inductive bias for the model to learn. So the model basically doesn't have enough knowledge to start with, so it will also not have good performance. So there is this type of optimum point, like somewhere here, where the symmetry in the data matches the symmetries in the model. But the difficult part is that we don't know how much symmetry is in the data. Right? So then we start asking this question, like, okay, can we somehow interpolate this regime, right, where we have models like, I don't know, GPT-3, which have little symmetry, or models like fully equivariant networks that have perfect symmetry, but can we interpolate between these two regimes such that we have a way to find this local minima? Okay, then this is kind of the mental picture that we had when we started this project. So here we're looking at model equivariance error, which is how much symmetry in the model. And here we're looking at how much symmetry in the data, right? And then naturally we will know that if for a perfectly equivariant model, because its symmetry doesn't change, so it doesn't matter how much symmetry we have in the data, the performance is probably always be the same. And then for models with no symmetry bias, right, because it doesn't actually use our domain knowledge or as an inductive bias, so it may not have the same power as other models, like symmetric models. But then there is this type of model that we hope to develop, which is something that can interpolate between these two, so we call it approximate equivariant models. So this picture you have seen in the morning. Thanks again, Tess. So here we're looking at a very, very simple example. Right? In the top row, you can see that, okay, the density, this is a heat equation, forward simulated. And it's obvious it has S2 symmetry, right? When you rotate, then every density looks the same. But in practice, the metal may not be a uniform density, right? Some part of the metal is depending on the thickness or the material, then the density, the heat will actually have this kind of asymmetric behavior. Okay, so then given this phenomenon, let's define like a more general notion of approximate symmetry. It is actually very simple, where we know, equivariance is defined via equality, right? Well, let's relax it. We can make equality as inequality, and then we can say that, okay, if my function f is approximate equivariant, then I can upper bound this between this gap, between these two terms, right? Essentially, if I transform the input with some group transformation, and then I will measure the difference in terms of output when I also transform the original function by the g. So if this gap is some constant, epsilon that's larger than 0, then this is approximate equivariant, right? If epsilon is 0, then a function is perfectly equivariant. So this constant allows us to control how much symmetry we need to have in this model. So this is a very simple and straightforward definition of approximate equivariance. We're not even looking at like probabilistic regime here, right? You can always say, well, I can always make it more general, like say with high probability, this thing is smaller than epsilon. We will leave that for future work. It's probably for people who are very good at the Monte Carlo sampling.
It's just for the norm on this thing though, you're just doing kind of like you do some kind of like L2 in this natural space.
Which is very simple. For our case, we just use L2 norm on the vector field, yes. But you can, I think you can use more general metric, all right? You can use Minkowski or like other norms or learn the Mahalanobis distance, depending on like the space of functions that we're looking at. We started here very simple, yeah.
I'm just saying, like, if they're all like in the abstract way, these are all like group valued things, and like the norm is kind of like not the most
it's not well
thing.
defined.
Yeah.
That's right. That's correct. So yes, but we're in a very simple setting here. Okay. All right. So then we can review what perfect equivariant networks should look like, right? As I mentioned, like to design equivariant networks, you basically need to solve linear constraints. But to solve linear constraints efficiently, there are different ways. Right? One is that you can do this type of people call like group convolution. So let's think about the image case, right? Okay, so h is my input, which is two-dimensional coordinates. So h is an integer number of x, y. That's an integer number. And then when we do convolution, I just move this filter across different positions of the image, and then I aggregate over different positions. You can generalize this, right, where h is an input in a group, and then we can aggregate elements over the group, and then k is a kernel that takes the inner product of the group and the input. So this type of computation directly generalizes the notion of convolution for translation. It is convenient or efficient in a way that it doesn't need to pre-compute the equivariant kernel basis. I think it has mentioned the Clebsch-Gordon decomposition and spherical harmonics. So these are belong to the second class of implementation for equivariant convolutions. They can be computationally expensive for certain cases, but here we're using a much more computational efficient way to compute group convolution. But then the downside is that you need to basically focus on the sum here. So you have to shift the sum over all the group elements. If the group is basically continuous or non-compact, then you cannot do the sum anymore. So there is limitation for computing group convolution in this way. So the second way is, coming from Max's paper, is a steerable, right? So steerable is you basically pre-compute this kernel basis first. So instead of doing this group aggregation, group summation over hard measure, you basically compute this, kernel basis first. You compute this first, pre-compute, and then afterwards you left multiply, right multiply the matrix. So this is people call the steerable convolution. Again, these are two different ways to implement perfectly equivariant networks. So now I'm going to show you how we can actually relax these two techniques using our definition of approximate symmetry, approximate equivariance. Right? So So again, our technique is very straightforward in the sense that, okay, we know, let's say group convolution, right? We have summation over group elements, and then the filter over the input, and then the kernel. But the kernel is shared over all the inputs, so that's how we obtain perfect equivariance. But then here we can say, let's break the symmetry by making the kernel dependent on the G and H pairs. So G is a group, H is the input, and then we can make K different for each pairs of GH, right? And then instead of using one kernel, K, we introduce L kernels L. So this basically gives us a way to tune the amount of asymmetry in the implementation. So if I have one L, right, let's say L equals 1, this reduces to the original perfectly equivariant networks. And if I have more L, right, then I will have more asymmetry in the system. So this is a linear combination of kernels. So W here is a scalar coefficient. This thing actually can be dependent on the input as well. So think about the image here. H can just be the XY coordinate on the image, right? And then this is saying that we can assign different weights to different coordinates. So this actually relates to this type of local weight sharing in graph networks where you have different weight parameters in different coordinates, like local neighborhoods. So this kind of like has this kind of subtle relationship here. And then this is how you can relax the group convolution. And then for steerable convolution, we can do pretty much the same thing, right? We can say that, okay, before we pre-compute these kernel bases, and then we figure out the group representation. And then before we use one kernel to compute this equivariant convolution, now let's introduce more symmetry breaking terms. So we have L kernel for this middle term, and then we assume this kernel is actually the linear combination of kernel bases where these coefficients of the linear combination are dependent on the input. Okay? Yes?
Just a quick question on that, or clarification.
Yes.
So, like, for example, if you were starting off with, like, spherical harmonic kernels, is it that you would add different weights to the different M's of the spherical harmonics, or that you would rather, like, have additional, or yeah, I guess, like...
I think when you say M, do you mean different harmonic basis functions, or?
Yeah, within the, like, set of L.
Yes, I think in that case, so you put basically here, right? So then if you do I think, let's see.
So, yeah. Okay, could I just, the same, it's either that or the thing I had in mind was just like a bunch of different complete spherical harmonics, but with different, like if you chose a different XYZ coordinate to expand around originally, like are the KLs would be like each one is a good spherical harmonic basis, but they're just not the same one, and then you're weighting them together in a way that's not.
So I think here you could be like let's say the angles or the right. That you have different angles, then you can make the coefficients of your framework depending on the angles. So
I see.
That,
okay,
yeah.
okay. But would you still apply that to, like, would you apply that coefficient to all the M's within a given L, or would you break it even further?
I think here we're just using the same.
The same.
Yeah,
so you
but
still weight share across the M's, but what that coefficient might be will be angle dependent.
I think so, but I need to double check with you on
yeah,
the actual mathematical notation. Yes.
I also have a question. So is this the condition that you're trying to solve? Because then K and K tilde are not the same, right? So how is K? So this is the definition of K tilde in terms of the case. But what is the condition on K, KL, in terms of equivariance?
Right. So in this way, we can still solve it in the linear equation, right? And because of this like kind of relaxation in case, then sometimes when we actually solve them, there is a gap between the perfectly equivariant. Well, we actually need a gap, right?
Do you solve this equation? But if you solve this equation, then K tilde needs to be related to K. Otherwise, it's not a constraint.
We don't solve this. Actually, here these are all learned. These are like the output of a neural network. So W, for example, W.
There's no equivariance constraint that you're imposing.
But KL is basically the equivariant basis.
Well, each KL is an equivariant basis.
Each KL is an equivariant basis, and each W is the output of a neural network.
But then is a linear combination of equivariant bases not again perfectly equivariant?
Well, because here KL was dependent on GH, right? If it's dependent on GH, then it's not perfectly equivariant anymore.
Okay, so we should talk later.
Question on this. So you had the constraint that the difference should be less than epsilon. Is there some way to frame this such that
Like
some
find
constraints?
analytical equations, or?
Yeah, you were trying to say I want it to be only a little bit non-equivariant.
Yeah.
Is there some constraint you can put on W, or do you put some constraint to guarantee that?
Okay, you can. In this case, you can tune L. So like, the bigger the L, the more not asymmetry you have.
But
So-
even with 2, couldn't you get arbitrarily far away from an equivariance? Couldn't you break your epsilon threshold in this?
That I'm not sure. We haven't tried that.
Okay.
Yeah. Yes, I'm not sure actually. So, so because if you have a fewer number of L's, then I doubt it will span the entire space of non-equivariant functions because of the constraints we impose on K.
But WL of H can vary arbitrarily by H.
But they're only, H is the input, right? But then the WL is just a two scalar. If I L equals 2, it's a function of the input.
Yeah, but it can be arbitrarily large, and and go arbitrarily large. Seems like you could break that, but it's okay. It probably is a.
I'm not entirely. Yeah, I'm not entirely sure. Actually, that can be possible. Okay, so then, I wanted to show you this a picture, right, where we wanted to forecast the dynamics of a smoke. So basically, depending on the inflow location and the amount of inflow, then we can break the symmetry by a different amount. So the more inflow you inject into the smoke, then the more asymmetry we inject into the system. So here we're looking at the prediction over time from time equals 1 to time equals 20 over different methods, right? So the left column is a ground truth, which is what we wanted to predict. And then ConvNet is a baseline that we treat as no symmetry. And then, because this is actually not rotational equivariant, right? Here we're looking at SO2. So ConvNet, it doesn't have SO2 symmetry built in. We treat it as a baseline without symmetry. So RPP is actually a baseline from Andrew Wilson's group. They use this idea like residual pathway to have an additive structure of equivariant and non-equivariant models. And UCLA is from Max's group, I think, and then basically it's a perfectly equivariant networks. So what's interesting here, these are basically two variations of our model, like our steerable CNN is a relaxed steerable CNN of our model. So then here we basically can see that the E2 CNN, right, the perfectly equivariant model actually completely get the direction wrong. The smoke should bend to the right, but then the actually predicted smoke bend to the left. So it shows that if we, because the data is not perfectly symmetric, and then we are imposing this strong constraints as SO2 symmetry, so the model is actually learning the wrong thing. The prediction is actually very far away from the ground truth. So this kind of shows the potential risk of imposing the wrong type of inductive bias in the model. Whereas in some cases, we can see that, our method does predict the direction of the smoke quite well. The limitation is that it doesn't capture the small scale behavior. Like actually in C2CN, it captured this small eddies quite well. But in our case, we somehow get this smooth velocity field. So that's the one limitation we can see.
So I got to look, the example is not rotationally symmetric, but the symmetry you want is on the solutions or something, right?
The data is not perfectly symmetric for SO2, right? Because you know that this type of dynamics is not perfectly rotational equivariant. It's not perfectly rotation symmetric because of the flow injection.
But it feels like there's a version where you could say the physics is rotationally symmetric, but my initial condition is not. But I thought the condition, at the beginning you were saying the condition is more if I have a solution and then I apply this symmetry, that it's still a solution. It seems like
That's from the PDE sense, right? But then again, like Navier-Stokes equation doesn't have rotation symmetry from the solution of the PDE sense. Rotation symmetry is not one of them. But here, here the way we understand here is just like the data itself, right? The forward dynamics, if you look at this data, the velocity field of this data, we wanted to have SO2 symmetry, but it does not. Yes, Tess, you have a question?
Yeah, so the inputs are like 2D vector fields?
Yes,
And so you're predicting like going from one vector field to another vector
yes.
field? And is it that the injection system is like you continue injecting additional energy into the system? Or like, yeah, I think I'm also not totally sure I understand in which way it's...
This is a simulated smoke. So we have external force, right? The external force is applied to the smoke at every timestamp.
I see, okay. So there's an additional force.
Okay, yeah.
Okay. That's
I
Sorry, I didn't know
Yeah,
that's what you're asking.
Yeah.
I just thought it was like you're squirting it in with some initial condition, and then it's just fluid dynamics.
I see.
And I was like, it seems like it's pretty rotationally symmetric to me, but yeah, I understand that. Okay, sorry.
Sorry, I didn't understand the question.
No, I didn't ask it well. Sorry. Yeah.
Okay, so the symmetry breaking comes from external force. And then depending on how much force you exert on the flow, you obtain different amount of symmetry breaking. Okay, then this is a picture that we wanted in the beginning. Right? And I think we're very excited because actually the picture kind of looked like what we wanted. It's actually not, it's simulated, but I think it's still pretty interesting in the sense that, okay, the perfectly equivariant models doesn't change behavior as we inject a different amount of forces. So that's expected. And then our steerable CNN is kind of reflecting how much symmetry we have in the data. So you can see that the optimum obviously is a diagonal line. So we still have quite a lot of work to do to bring this green line to this dashed line. Right? So the model is not recovering exactly the amount of symmetry we want. I think that's probably like related to how we actually solve the equation, as Max mentioned. I think there is some nuances on how we solve the equation, so it's not like matching this optimal line. Okay. Then this is the result that I mentioned, that we apply this to real-world turbulence of supersonic jet flow. So the data we got from NASA, now it's open sourced. So it's a 2D turbulent velocity field. It's captured using camera. And then we wanted to predict the future flow because they don't have a good equation near the nozzle, so they really don't know how the turbulence will evolve at the next timestamp, but they want to have a model that can learn from this data. So then here we basically apply our method to this data set to forecast the turbulence, right? So just look at the rotation, we can see that if we use the relaxed equivariant network, it is 20% better than strictly equivariant network, which is not surprising because the real-world data is never perfectly symmetric. This is just the residual visualization of how the predicted values should evolve. Like, for example, this is the error visualization. So closer to the zero, the better. So the more white it is, the better. So you can see that different versions of steerable CNN basically have quite accurate prediction, so with low error compared to other baselines for this real-world data. Yes?
Sorry, I missed how this is a 2D flow. You said this is a 2D, you're taking a slice through the street.
We're taking slices, like taking pictures.
And so the goal is to predict from from this slice's contents at
Yes.
time t
Yes.
to this slice at time
Yes.
t+1. But isn't that affected by whatever turbulent stuff is going on over here? It's not like a constant force over there, right?
Well, it is kind of like, it's evolving because it's a supersonic jet. There's a one directional force, right, coming from the engine.
Right, but you're like picking a fixed physical slice.
We're looking at because we're like mimicking the camera where you're just looking at the particular position of the flow.
Right, but it's getting kind of its effect over time is some chaotic turbulent process, right? Of that effect. So
Yes.
it's not a constant effect either. I see.
Yeah. It is a simplified setting, but we talked with people in NASA, then they said the results make sense to them. So, okay. All right, so then I guess the last part of the talk, I wanted to talk about this new work, which is actually a little bit different from like using symmetry to learn complex dynamics, right? I mentioned like spatial-temporal dynamics. Then these dynamics can come out of turbulence, can come out of molecular simulation, but actually it can also come from the training of deep neural networks. Right, so this is like a picture I used it in my class as well. So you can just watch how the gradient changes in this this is the landscape of a deep neural network. And then we can just watch how these different optimizers change, evolve like particles on the surface. And then, we can treat this itself as a dynamical system, right? Then we can ask the same question, is like, can we exploit symmetry in some sense to learn this type of dynamics and hopefully make it better? And so this work was led by my PhD student, Bo. When she started, I gave her this task. It's like, we have been doing a lot of work on learning dynamical systems. Can we think about the other way around where we're understanding the dynamics of learning? So she took on this challenge. So I'm very happy that she's really making progress under the help of Nima, our great collaborator. Okay, so the motivation, as everybody know now, is deep networks are extremely hard to optimize, right? And then the landscape of deep network. This is a 2D projection, so this is very complicated, highly non-convex problem. So it's very hard to optimize. Then the question is, well, can symmetry help in this case? So we are thinking about what typical optimizer look like. So what they do is they usually make this local updates in the landscape of optimization. So you do gradient descent, or if you use Atom, you have like some momentum that pushes this type of this variable through into a local valley. But then sometimes it doesn't utilize the geometry of the landscape well. So that's one limitation of gradient descent. So naturally, there's the second order methods like Newton's optimizer. So the Newton's method is faster in terms of optimization sense because it actually leverages the landscape of this optimization surface, right? So it basically have this preconditioner term in the Newton's optimizer that it is the scaling term related to the shape of this manifold. But then the challenge of second order methods is that it's very expensive to compute. It's hard to compute the Hessian of a very large deep networks. So we were asking the question, like, can we find a cheap method that can mimic the behavior of second order method, but operate like a second order method? So that's basically this algorithm, which we call teleportation. So this algorithm utilizes the symmetry in the landscape of optimization. So essentially, if we are looking at this landscape, right, we can see intuitively that if we start from here, and then if we just do gradient descent from this point to the local minima, it will take a long time. But however, if we start from a different position, and then doing gradient descent along this direction, then it's obvious that this direction is shorter, so it will take less time to converge to the local minima. So if we can make a big jump from this point to this point, then we potentially can accelerate optimization in this sense, right? And this idea of making big jump is quite different from the optimizer that we use today in deep nets that makes local updates. Here we're looking at the global landscape and making big jumps in the landscape. Okay, so then basically this is our symmetry teleportation algorithm. So we start with a general loss function, and we have some learning rate, and then we initialize our parameters, right? So this is like here, we start from here. Let's say we have the variables, or the parameters of a neural network at time t, and then we can just do regular gradient descent, but here we wanted to make big jumps along the landscape, so we have this subroutine in the optimization algorithm that allows this variable to make big jumps, which we call teleportation. So if you look for more detail into the subroutine, you can find that we wanted to basically transform the parameter of time t, wt, to a different position, but along the level set of the landscape, which means the loss actually doesn't change along this teleportation. So then in this case, we're using symmetry because we can apply group transformations to the parameters. And because the loss doesn't change, so it hasn't affected the loss so much yet. Okay, then the difficult part is this subroutine, which is to find a group transformation that belongs to the symmetry of this optimization problem. So this symmetry is different from the typical symmetry we talk about in equivariant networks, because in equivariant networks, we're talking about symmetry with respect to the data. But here we're talking about symmetry with respect to the parameters of the model. So we're utilizing the symmetry in the parameters of the model to make these big jumps. And then afterwards, we can just do regular gradient descent to do local updates. So then I want to talk a little bit more about how we can make big jumps on the landscape of optimization. Right? Okay, this is the animation. We make big jumps and then we make updates. So how do we find the teleportation destination? So we want to solve this argmax problem. The objective function here is that we want to find a group transformation. So the set of group here, G, it should belong to the symmetry of the network. Right? So G is the parameter symmetry of our model, and this gives us a level set of the optimization landscape. And we wanted to find a transformation such that the gradient of the loss is maximized. So it gives us the steepest direction that we can make descent along, and then we find that group element. Okay? Any questions?
The group is just following sort of the loss function in where it doesn't change. So
yes, the level
it's
set.
A very general diffeomorphism or something like that.
Yeah, we haven't thought about diffeomorphism, but yes, we're basically the group is just the transformations that doesn't change the loss.
Yeah, but it's not actually a group. It's just basically saying I'm just going to. I mean, any vector can be decomposed in a direction that goes down and the direction that is, and I'm just following
what we call the symmetry direction.
Yeah. Okay.
But I mean, I could imagine that your network actually does have some symmetry, so you know that there are some parameters you can change that would is a property of the network, and then there's a part which is just generally this is a flat direction in the loss.
In fact, we actually use a very general GL group in neural networks. So we actually
but the way you're using it is just the direction where the loss is constant.
That's right.
Okay.
The reason I said group because we actually parameterize this set. We can parameterize this family. Yeah.
So, if you could go back the slide before, so are you doing it in an stepwise manner that first you are projecting to the steepest direction and then finding what happens if you do it together, that your loss is a combination of finding the steepest direction plus symmetry regularization?
And we're changing our optimization problem, right? Yeah.
Just doing this teleportation can send you to very different minima. There's no guarantee you're going to get to the same minimum by doing this.
There's no guarantee it will lead to the same minima for non-convex functions. Yes?
So if you know the symmetry, couldn't you just project the optimization problem onto the non-symmetric part?
What does that mean?
Like project out the parametric degrees of freedom that are symmetric.
Are you saying that instead of optimizing all this landscape, we find another manifold and then optimize on the other manifold? But that projection itself is very expensive, right? And you have to do this, you have to do this like push forward and then like push back. It's very expensive to do this.
Can you add like something like momentum here to?
Yes. So we actually have done that before. Great question. That's okay. So then. No questions for this, right? Like subrouting? Okay.
Are you going to tell us how you do the argmax?
Huh?
Are you going to tell us how you do the argmax?
Yes.
Okay, yeah.
Okay. So there are some techniques that we proposed in this paper. How do we do argmax, right? So essentially we can parameterize this actually. So if the G is a continuous group, we can parameterize a continuous group, right? Let's say if it's a SO2 group, and then we know there's one parameter that parameterizes SO2 group, which is the angle. Then because of that, we can do gradient descent within this group. So the argmass is actually solved with a local update algorithm. And you can actually solve it with any optimization algorithm if you parameterize the continuous group.
But does that not get you back into a second order method?
Because
you're doing a grad of a grad or not? That's the part that
yeah, but we don't need to compute the inverse of the Hessian.
Okay, but you're still taking another derivative.
Yes.
Yeah.
Okay, and then for general linear group, right? For general linear group, we can look at a general continuous group as a Lie group, and then this picture just shows like if we have a group like a group manifold, and then we can actually take infinitesimal approximations of any point on this group manifold that give us a Lie algebra. So for continuous group, then we can actually parameterize the group as Lie algebra, and then in practice, what we actually implemented is a first order approximation of the algebra for continuous groups. So then again, because it's a continuous group, we can do gradient descent on this manifold of group elements. Does that answer your question, Kyle? Okay. Okay, I can show you some experiments that we did. So this was some test functions in non-convex optimization community. So it's like benchmark functions in non-convex optimization community. One of them is what people call the boost function. So it looks like this. So it's elongated along one direction and then very narrow along the other direction. So this trajectory shows the path of gradient descent using local updates coming to here. And each point is the position of the gradient as a variable at each iteration. So then here we can see that if we do teleportation, where we make big jumps, right, then it will actually make big jumps towards here. So you can see it's actually not exactly the level set. Like this point, when we do big jumps, the teleportation, the orange step, it's not exactly the level set we want, but it's like a slight approximation when we do gradient descent in the subroutine. But it's good enough. It gets good enough get us to this better point, and then we can do gradient descent. And this way, we basically require fewer number of iterations in optimizing this function. So then we can also measure, right, the training curve of this algorithm. So this is only we're only talking about optimization, right, which is training. We haven't talked about generalization yet, but we actually just submitted a paper to ICML about in fact, the teleportation has benefit in generalization as well, because it gives us basically a more flat minima, because the sharpness of the minima relates to the generalization power of neural network. And then if we do this kind of teleportation, it does give us flatter minima. But this is not included in this paper. So this paper was just saying we're looking at optimization, and then we can see that optimization-wise, this is faster. Right, because we can do big jumps, so this is much faster.
But do you include, let's say, the additional step in a time step?
Yes.
But is that fair? Because you can do many steps downhill for the same computation that you have to do for that surge.
We measured the wall clock time. Yeah, as well, they're comparable. They're very comparable because the subroutine, the gradient descent is very cheap compared to like computing the Hessian second order. Yes, that's a great question. So then here we're also looking at another test function like Rosenbrock. So Rosenbrock function is like it's a weird shape which has a valley in the landscape. And then this is kind of the minima we want to reach using gradient descent. And then if we do big jumps, then we can, so this is the same number of iterations. And then using the same number of iterations, then we can reach the local minima faster than gradient descent using teleportation. So then we can also looking at in the training curve, then we can see that when we do big jumps, so you have this huge loss drop along training loss, then it is faster. And then we look at multi-layer neural network as well. So for multi-layer neural network, this is a relatively simple toy neural network, right, with nonlinearities. So here we can see that if we use a gradient descent, which is a blue curve, when we apply teleportation, it drops faster. the loss converges faster. And we also apply that to AdaGrad, adaptive gradient descent, and we see similar phenomenon. So this is the wall clock time. In some cases, right, the teleportation actually is not sacrificing a lot of time in terms of computation. And this is basically measuring the norm of the gradient with respect to how the loss changes. Because when we use teleportation, we're essentially seeking the direction where the gradient of the loss is increasing. So we can see that in teleportation, these two colors, then the norm of the loss is actually increasing as expected. So teleportation does give us this advantage in finding better directions to go down. Right? Okay.
That example.
Yes.
I'm sorry. What was the dimensionality of the? I mean, you're doing still SON.
This is GL. It's a GLN.
Okay.
The GLN. Yes.
And what is the dimensionality of all of the parameters?
This is actually very small. I remember it's maybe like less than 10.
Okay.
Okay.
Have you tried with the ConvNet on image dataset?
Yes, we did. We also have experiments on MNIST. Yes, but MNIST is just like a toy data. We're working on. We have a new paper about more complex neural networks. Yes, but we feel this is like a starting point for this algorithm. Yes. Okay. So more symmetries, and then so I talked about free work, right? This is work led by my student Sophia. This is trying to do like a symmetry for the probabilistic space. And we actually looked at very detailed in Frank's paper on equivariant flow models. We wanted to look at forecasting of autonomous vehicles. So this is the trajectory of the autonomous vehicle in real world. And then we wanted to be able to generate this type of uncertainty for trajectory prediction, because uncertainty is very critical for decision-making or control algorithms. Then we use symmetry to improve uncertainty quantification in multi-agent dynamics modeling. We also use symmetry to discover symmetry. We have some early work with NEMA to discover symmetry using Lie algebra generators. To conclude, so I talked about including symmetry for learning spatial temporal dynamics. So EquiNet is symmetry in differential systems. Relaxed equivariant is really trying to bridge this gap from simulation to real. We have approximate equivariant networks. And I talk about teleportation, which is a new direction that we're thinking about to use symmetry for accelerating learning dynamics. There are more to be done here. Symmetry discovery, tests as work on E2, E3, CNN, asymmetry. Asymmetry is a very interesting topic. So there's more to be done. A final slide. My talk has nothing to do with molecules. And then when I was invited in this talk, I was very nervous. I was, okay, what should I do? But I do have one project related to molecules, so you can just scan this. And you will see what it looks like. It's actually an interactive interface for people to design molecules using our generative model. So we can generate molecules and allow you to score them. And then we are building an active learning backend before this algorithm, so we will really hope you can give us some feedbacks. So okay, so then you can find the code in my website and Twitter, and here's the funding agencies for supporting this work.